So, hi everyone, welcome. Thank you for coming to this kind of my part of a split up thing. I'm going to be talking mostly about software-defined radios and kind of an overview of how they work with a view for kind of really very much beginners, people who roughly know what radios are and maybe why they're interested in a software-defined radio, but don't know anything about how they work and aren't necessarily particularly mathematically inclined to find out why either. So I will be using as little kind of maths as possible. If at any point you think I'm simplifying something too much and you would like some more detail, please shout. Or if you don't understand something and I haven't simplified it enough, likewise, just say so. There aren't enough of us that it will be disruptive, and I'm very happy to kind of go over something a bit more slowly or speed up if you're really bored, I guess. Okay, so the only things I'll really assume you know beforehand are that we're interested in radio waves, which are some kind of magical waves passing through this ether that surrounds us always, and we're interested in doing something with them. Most of what I'll say will be about receiving these radio waves, and briefly I'll mention how everything runs the same in reverse to transmit. So keep that in mind, I guess. Okay, so I'm going to kind of split this into two halves. First of all, I'll talk over kind of, in theory, how these software-defined radios work, roughly what kind of building blocks go on inside them in the kind of most obvious detail possible. And then a kind of diversion to this IQ sampling concept, which is a kind of scary sounding name that maybe you've come across, maybe you haven't, and I'll try and motivate why we want to use it. And then after that, I'll just do a whole load of demonstrations. I've got a bunch of different software-defined radios with me and some software to run with them, and we can kind of see how they work and why they're useful. Cool. So, I guess I didn't prepare slides, so instead you can be treated to some hand-drawn diagrams. Excellent. So we start off with some kind of radio wave, and we want to receive this. So hopefully you're aware that we have this thing called an antenna, and it turns radio waves in this mysterious electromagnetic ether into voltages on a cable. So here's our antenna. The voltages have some frequency, and this is how fast they oscillate. In this case, you can see it's kind of going up and down. If it goes up and down very quickly, this is a very high frequency. If it's quite slow, that would be a low frequency. These frequencies are really important to us for a number of reasons. Computers can only run so fast, like they're typically clocked in gigahertz, and maybe you can operate on a few hundred megabytes a second, which means that when our radio waves are very high frequency, 3 or 4 gigahertz, 5 gigahertz, you need to somehow operate on them to make it useful. So first of all, our antenna receives this signal, and we want to, and it turns it into this oscillating voltage on the cable. We can generate those locally as well, and without going into much detail, it's fairly simple to have some kind of clock source which outputs some sine wave, I'll say sine wave or signal pretty much interchangeably, some kind of oscillating voltage at whatever frequency we desire. And I'll call this the LO, which stands for local oscillator. Because it's our locally controlled clock. We control what frequency this runs at, unlike the signal coming in off the antenna, which is what we want to receive. And it turns out, through a very convenient, fact of life, that if you multiply your incoming signal with some signal whose frequency you control, you can influence this frequency at the output. Specifically, if this was at some frequency F1, and this was at some frequency FLO, then the output will be at frequency let's say F1 minus FLO, and also F1 plus FLO. And this is kind of the real key building block to most radios, but especially software-defined radios, where we have some local oscillator we control, and because we can tune that to whatever frequency we want, we can tune what frequency we see on our receiver side, independent of what kind of frequency we were trying to receive. So, that's a nice trick. you'll notice that we have two signals at the top, two different frequencies, and typically we're interested in one. For example, if this frequency was a typical balloon at 434.650 megahertz, chosen specially to annoy repeaters, and that's F1, then we could set our local oscillator to 434.649 megahertz. And hopefully you'll believe me if I say this is then the difference between them, which is 1 kilohertz, which is really useful because you can feed that, say, directly into a sound card. It's an audio level frequency, and your computer can deal with things coming in off a microphone port, no trouble at all. So this is exactly how, for instance, DLF or Digi works. We have some local oscillator at 434.649 megahertz, usually your ham radio, say, and the output is at 1 kilohertz, which DLF or Digi can process and do its magic on to turn it into a message from a balloon. The problem is that we also have this frequency, but you'll see that if you add those two together, you have something like 868 megahertz, which is a very large frequency and consequently quite easy to filter off. So this idea of filtering is we'll let through some frequencies and not others. So this is kind of the next block we need, and this is a low-pass filter. So the output from a low-pass filter will be just a 1 kilohertz signal, which is what we're interested in. Finally, we need to send that signal to our computer somehow, so we use an analog to digital converter. If you haven't heard of this before, it's roughly what the name suggests. It turns an analog voltage on the one side into some digital number on the other. So typically, for instance, it might output a number between 0 and 100 to the computer, and its input might be between 0 and 1 volts. Then half a volt would give you 50 on the computer side. So we have some ADC here, and this goes to your computer. You may have used an ADC before, like an Arduino has a few of them, and you can use them to read light sensors and temperature sensors. The ones we use in software-defined radios will typically be quite high specification, so they can sample millions of times a second instead of, say, tens or hundreds or thousands of times a second. The faster they can sample, the kind of more useful they are to us in this situation. So that gives us a kind of basic building block for a software-defined radio. You have some kind of antenna, this multiplier, which we call a mixer, but really is essentially just multiplying the two signals together, some local clock which we control, or local oscillator. The output here has a frequency we don't want, so we filter that off. And then we convert this to some useful number for the computer. And then this goes off over a USB cable, say, into your computer. And there are some more details, like usually you have an amplifier in there to boost the signal level. You probably have some more filtering, but I decided they probably weren't very important to get a basic idea of what's going on. So this is quite nice, and you can imagine it works quite well if you've tuned to, in our example here, 434.649 megahertz, and your signal is slightly above that, then you'll receive it at 1 kilohertz, and that's fine. There is an additional complication, which is if that input signal starts going down and down in frequency, as balloons are wont to do, it will eventually be the same frequency as your local oscillator, at which point the signal coming out will be at 0 hertz, DC. It will just be flat. There'll be no oscillation. And it can then continue to go down in frequency until it's below your local oscillator, and then the difference is negative, so it has a negative frequency. This complicates matters, A, because negative frequencies aren't something you usually expect to come across in day-to-day life, and more importantly, B, because they are indistinguishable in this setup from a positive version of a frequency. For example, if you just had some wave at this frequency, the negative frequency really, it looks the same. So you get 1 kilohertz out just as before. This is a problem if you want to know which frequency your signal actually was. Right now you can't distinguish them, and for various other reasons this will mess things up. So we want to somehow find a difference between this positive and negative frequency. And the one kind of key trick to this is that they do differ in one crucial element. This is one of the only equations I'll write, and you don't really need to know it, but maybe you'll remember from school that sine of negative x is actually equal to negative sine of positive x, which means that, strictly speaking, if you did have two sine waves and one was positive frequency and one was negative frequency, they would have opposite phase. This is like 0. So the idea here is that if we could somehow work out the phase of a signal that we receive from a mixer, in addition to like its current amplitude and frequency, we'd be able to tell whether it was originally at a positive or negative frequency. And that's really important for being able to do most digital signal processing with a result. There are ways around it beyond the normal technique, but... So, right, I think probably this whole business of why we need to detect negative frequencies and what that really means is one of the more complicated things to get across. Occasionally I'll be reading someone and suddenly think of a new way to understand it, and there are a million analogies. So I might try a couple and then see if any of them stick, and if you still aren't sure, feel free to ask questions or ask for clarification. So, right, I said they have a different phase, and that might not be a term you've come across. So, just briefly, the phase of a signal is kind of how far along its cycle it is. So, for instance, if I drew these same waves at the same frequency, and one of them looks like this, and one of them looks like this, they're just shifted in time. And that shift is the phase between the two of them. So they're at different phases right now, these two signals. And we want to somehow measure that. The same is true of the ones over here, where they're exactly 180 degrees out of phase. You can see the bottom one is just this signal, but starting in the middle here. So we measure phase in degrees typically, and it goes from 0 to 360 degrees. So 360 is the same as 0, and 180 is exactly the opposite phase. Right. So how can we really measure that? If we think back to what the ADC does, then at any moment in time, it records the analog voltage it sees. And we know that analog voltage is oscillating up and down. So really what we record is, if this is time, at several moments in time, we record the amplitude of the signal, and that's the number that we save. So, in a sense, we can know what the phase is at any moment in time by that amplitude. If it's a high number, then the phase is right here. If it's a low number, then the phase is this far across the cycle, 3/4 of the way through. And having recorded that, we can work out the frequency quite easily. Obviously, if this takes 10 cycles to complete and go back to 0 phase, then its frequency is 1/10, say, whatever that corresponds to. And if it takes twice as many samples, then it has half the frequency. So, in a sense, phase is the kind of really important thing we want to actually measure here. So, before I explain how we measure it, I thought I would have a quick demo of what this actually looks like with some real signals. So this is a piece of software called GNU Radio. You may have come across it before. It's quite nice because it can both talk to real software-defined radios quite easily and also lets you simulate things on your computer really easily. So in this case, I've just got an empty spreadsheet, an empty flowchart, and I will add some signal which is going to represent whatever comes in off our antenna. And we can choose what frequency it will be at. So I'll just set it to some variable called frequency. And then because we want to control the frequency, we can just add a little slider on that lets us set this to anything we want. So in this case, we will start it at 1.1 kilohertz. And then we add our multiplier. I mostly have to change these from complex to float. Float just means kind of single dimensional, which is all we're thinking about at the moment. Then we can add our local clock. which I will just fix at 1 kilohertz. So this multiplies these two together. We add a low-pass filter, which gets rid of the high-frequency component. This has the very, so we'll say, I don't know, 200. We can just tell it what frequencies it allows and which it doesn't. And then we want to look at the result. So we put a kind of oscilloscope, basically, on here. Okay, I'll just make it a bit clearer to see what's going on. The one downside to GNU Radio is there a lot of these option fields, and sometimes it's a little mysterious what any of them do. But, okay, here we are. So we have a slider at the top that controls the frequency of a signal we're receiving, and we can see at the bottom the signal that comes out of our mixer. And right now it's this is representing 100 hertz, and yeah, it looks like it's doing about 10 cycles in about 1/10 of a second at the bottom there, so I could believe it. We can control the frequency of the signal. So as I shift it down to 1050 hertz, we now have a 50 hertz output from the mixer. And as it gets closer and closer to the local oscillator frequency, you can see the frequency we receive gets lower and lower and lower, until eventually it's exactly the same frequency, and this is just DC, there's nothing here. You might expect a completely flat line, and the only reason it's not is because the scope is no longer triggering. So as we then shift more and more negative, we start to see exactly the same thing we had before. So this is kind of a problem being demonstrated. Here it is at 950 hertz input signal, and here it is at 1050 hertz input signal. And you can't tell them apart as stands, which means they're ambiguous. So the way we resolve this problem is by taking an additional measurement of a signal, basically. We want to know its phase as well as its amplitude, so we have to record something else. And the measurement we take is, instead of multiplying it by this local oscillator, we take the same local oscillator and shift its phase as well. Nice. So previously we had some local clock, which looks like this, and we were going to multiply it with our signal. Now we have another local clock, which looks like this. It's the same frequency, but it's 90 degrees out of phase, which is the same as saying if our previous local clock was a cosine, then this one is now a sine. So we'll try that real quick. We add a new signal. This one we can set to be a sine wave, which gives us the phase offset we want. We could also just change the phase, but this is easier. And we'll get a new multiply block. And we multiply the signal here.
Can I just ask, why is it called the multiplier when it's actually adding and subtracting?
Yeah, absolutely. So it's, at a voltage level, the actual signals you see, it is multiplying. It adds and subtracts in frequency.
Oh, okay, so it's the amplitude that it's multiplying and the frequencies that it's adding.
So, I mean, you can just accept that. I could try and illustrate it. If you do have two sine waves and you multiply the values together at every point in time and they're slightly different frequencies, what you get out is a kind of messy wave that has two different frequencies in it. In fact, if I just disable the low-pass filter and connect the multiplier directly to the time sync, then here we can see what's in this. The output is both the original, the low frequency, which you can kind of see as a thick blue line, but also the much higher frequency, the sum frequency, is this whole load of sine waves going on just inside here at a much higher frequency. So that is literally just multiplying the two voltages together. And that just happens to give you the two different frequencies. If you can think back to trig identities at school, This is because 2 cos A cos B is equal to cos A plus B plus cos A minus B. Right, so it is a thing that happens to be true, which is quite nice for this. So I'll turn this back on. Take the signal and multiply it by our new local oscillator. Copy the same low-pass filter. And now we'll add a second input to our oscilloscope. And we'll just connect. Okay, so now what we see here is the output of the 2 different mixers, one at the original local oscillator and one when you mix with the local oscillator slightly out of phase. And they're both sine waves and they're both out of phase, so this isn't hugely surprising. What's interesting to note is here the blue wave leads the, well, lags, I guess. The blue wave appears in front of the red wave, and that happens all across. And as I shift the frequency down, the same thing is true. So for all of these positive frequencies, the blue wave appears slightly later in time than the red wave. If we go to the negative frequencies, they've swapped round. And this is kind of a key to being able to work out what the phase of our signal was and whether it was a positive or negative frequency to begin with. So because we now have these 2 different measurements, it's kind of, we have a bit more information, and that extra information is what lets us work out the phase of the signal. And it basically comes down to the fact that if it was a negative frequency originally, then you'd get this red, which is the phase-shifted local oscillator, coming a bit after in time the blue, which is the non-phase-shifted local oscillator. So like, even if we were just looking at the red one, the new shifted one, we still can't tell apart the positive or the negative frequencies. It's only when we have both that we can see which way around it was. So back to this. So that's basically the idea. We add one more local oscillator. We have our antenna again, and this time we're going to split the signal, and we're going to mix it with the out-of-phase local oscillator and the in-phase local oscillator. And then we filter these. And now we need 2 ADCs. And we send 2 sets of numbers to the computer. And now the computer can do its digital signal processing. So this is what's actually inside most software-defined radios. We'll call this one like cos FLO, and we can call this one sine FLO. So this kind of leads naturally into calling it I and Q, and by naturally I mean not at all naturally. This is the in-phase oscillator, so we'll call this the in phase, and you can almost see where this is going, but you're wondering which word starts with Q, and it's quadrature, which means out of phase, or at 90 degrees, I guess. And thus, this is the Q signal, and this is the I signal, and that's what goes to our computer. So our computer receives 2 streams of numbers. One is the I numbers, and one is the Q numbers, and they represent those 2 colors of sine wave that we saw when we were doing our mixing. So kind of what I'm getting at is we need to take this second set of measurements, because otherwise we don't have enough information to work out what our original signal really was. And this is one and by far the most popular way of taking that second set of measurements. When we have those measurements, we don't typically draw them as sine waves against time, because for most sorts of data that we might be interested in decoding on the radio, that's not a very useful way of processing it. Instead, we draw both I and Q at the same time on a single chart, which represents one moment in time. So if I draw a plot here, where on this axis I have I, and on this axis I have Q, then at any moment in time, the signal we receive is some I and some Q. So if in this case the I number was, 20 here, and the Q number was 10 here, then the point we have is this point here. And maybe a millisecond later, the measurements have changed slightly, and the point has moved up to here. And over time, that point will keep moving, and that represents the stream of numbers coming into the software-defined radio. And this is the representation we typically use when we're processing numbers. So I realize it's a bit more abstracted from the voltages of the sine waves, but essentially we're multiplying it by these two local oscillators and reading those numbers and plotting them like this. And it turns out this has a whole load of really easy, nice, sensible ways of interpreting it. So I promise this will be fairly straightforward. Here's our point that we receive. If we measure this angle, that is the phase of the current sample. And if we measure the length of this, then that's the amplitude. Which means at any moment in time, we know exactly what the phase and amplitude is. And now in our software, we can very quickly work out, okay, so right now we're at this phase, a few minutes later we're at this phase. And that kind of naturally leads to most ways of processing digital data. So if we think back to the sine wave that we had a minute ago, you can probably, yes, excellent. So we have these two sine waves and they're slightly offset over time. On our I and Q plot, we'll say the I in this case is the blue line, then it's looks roughly like this. And if we rotate and think of a Q line, it's out of phase against time, which means if we were to plot the IQ point, then at the first moment of time, I is at 0, Q is over here, our point is here. A short moment in time later, I has risen up to this value here, and Q has come down to 0 here, and our point is now up here. A little while later, I is back to 0, and Q is at a maximum over here. Our point has moved down to here, and so on. What this means is if your input is some sine wave, then your point on this IQ diagram will be rotating round in a circle, and how fast it rotates round depends on the frequency. So if you're looking at some IQ plot with some points spinning round and round and round, that represents some sine wave coming in. And we can do that pretty easily in GNU Radio. So we'll take, I'll keep the time sync for now, and we can add what's...
Sorry to be naive again. Why would those frequencies have changed? You've got them coming in from your signal and you're coming in from your oscillator. Why would any of those two frequencies have changed?
Okay, so they change if the signal you're listening to on the radio has changed. So if the signal on the radio is just a constant frequency, then that's exactly what you'll see on your side. And in this case, that means it will just be spinning around this circle.
Yeah.
But if the signal you're listening to changes slightly, for example, if it's a HAB and it transmits by changing between two different frequencies, one represents a binary 0 and the other 1, then when it's on the 0 frequency, it's at some spinning rate. And when it shifts to the 1 frequency, it will be spinning faster on your IQ plot.
Yes, I understand that, but what's commanding it to change frequency?
What commands the signal to change?
Yeah.
Well, whatever is generating the radio wave. So typically, this will be like a microprocessor on your balloon, sending a voltage high or low into a radio module, which then changes between two frequencies.
Okay.
And then that's what we're interested in receiving. In the HAB case, we want to know which frequency is it currently running at.
Yeah. So it's not Doppler or anything like that. It is a result of processing.
Sure. In this case, Doppler would have the same sort of effect. If the object was moving with some Doppler, then you'd see this shift in frequency as well, and you can't tell the two apart, so that can cause problems.
Yeah. Okay, thank you.
So we will have a Constellation Sync, which is a fancy way of saying it will plot the IQ points. And because of how GNU Radio works, it represents IQ data as complex numbers, which is really just a 2D number. A complex number just has two parts to it, just like I and Q. So we can wire I into one of them and Q into the other, and then hook up the Constellation Sync. And now if we look at it, right, we see this circle. If I slow the frequency down enough, you can see, so it shows the last 1,000 points, and you can see them slowly rotating around the circle at whatever frequency is the mix here, 8 hertz.
Oh, is this like a live running?
Yeah. Sorry, so the waves at the top, are running, but they're triggered off.
Oh, right.
So they always look in the same position.
Nice.
But yeah, the bottom is the rotating constellation points. If a frequency gets higher and higher, eventually it rotates quickly enough that we can't really see it. But at these low frequencies, it's kind of more clear what's going on.
So that's a tail of 4896 points.
Yeah, exactly. Then if we shift to a negative frequency, after it settles down, it rotates in the other direction. So this is because now the red line is leading the blue line instead of the other way around, which means just from looking at this spinning point, not only can you tell what frequency the input was by how fast it's spinning round, but you can tell whether it was a positive or negative frequency by which direction it's spinning in. So that's already kind of a start to being able to do some useful processing. Okay, but for a lot of radio modes, it's much simpler than spinning round. If we swap back to this, so if we have some IQ diagram, and we remember that the amplitude is how far away from 0 it is, so like this point has some big amplitude, and this point has some smaller amplitude, then many radio modes you might be familiar with, like Morse Code, where you just turn the radio on and off, are really easily represented. If a radio is on, then the point can be over here somewhere, or really anywhere on this whole circle, because they all have the same amplitude. And if a radio is off, then it's in the middle, assuming it's at just the right frequency, say. And that means if you want to decode Morse, you just have to know whether the point is in the middle for 0 or close to the middle, and on the outside of a circle for keyed. And then I guess you have to do your timing stuff. But so Morse is fairly straightforward. As I mentioned with the HAB balloons, we use something called frequency shift keying, where they swap between two frequencies, and we see that as two different rates of spinning around the circle, which is a little more annoying to decode, so often you do it in a slightly different way. But for a lot of really popular modulation schemes, such as Wi-Fi and GSM and pretty much anything going into space, most satellites, Bluetooth, you use this IQ representation a bit more directly. And you just say, right, here is our IQ plot. Then our transmitted signal will say either be at this point or at this point, and we'll call this a 1 and this a 0, and we can transmit binary by just moving between these 2 points. And at any moment in time, if we're at the 1, that's a 1 being transmitted, and we're at the 0, that's a 0 being transmitted. And then it's easy to make this a little bit more sophisticated. You can add 2 more points and say, well, if we're here, then we're transmitting a 2, and if we're here, we're transmitting a 3. And now you can transmit 2 bits per radio symbol. And you can probably tell where this is going. You could add some more points around the circle. And now you have 8 points, and you can transmit 3 bits per signal. Or you can stop using a circle, and instead of just changing the phase, remember the phase is this angle, so this signal has twice the phase. But because these points lie in a circle, they all have the same amplitude, you can instead have a bunch of different amplitudes, so you can make like a nice square or something. And then you pick one of these points and you transmit it. And this, as you can probably imagine, is really easy to decode if you have this IQ data. You receive some point, and it's like here. And you say, well, it's closest to this point, so it was probably the value 1101. And then you keep repeating that, and that's your data stream. So this is why it's kind of really useful, and why most software-defined radios work like this. The data you get in really naturally fits to how you tend to modulate your data when you're transmitting some binary over the radio. Yeah, for reference, this top one is called PSK, for phase shift keying, because you shift the phase, or this bottom one is called QAM, for quadrature amplitude modulation, because you change the amplitude and the phase together to get those different points. Right, so that pretty much wraps up what I wanted to say about the kind of how SDRs work before I got on to just kind of playing with some and showing you how you use them in anger. I wonder if I could... Yeah, so it is like £200 maybe. And it's a bit more capable. It can go faster, it's higher quality. Being able to transmit is nice. It can't transmit at the same time as it receives, and it takes a little while to swap between the two. There is this AirSpy, which is a bit more deluxe at receiving, but can't transmit at all, but is a little bit nicer. And then the other one I have with me is kind of wired up, this Blade RF, which is a chunk more expensive, but much higher performance. It can do maybe 40 million samples a second, big chunk of bandwidth. You can kind of do Wi-Fi and GSM and fake being a cell phone base station and all the rest. Plus it can transmit at the same time as it receives, which is useful on different frequencies as well. And that costs maybe £300. And then you can spend loads more money. Fancy ones cost upwards of several £1,000s and do all sorts of terrifying things. Cool, so the first kind of easy use is you run some application that does everything for you. And then you don't have to worry about GNU Radio or do anything fancy. In this case, there's a piece of Linux software called GQRX, which will hopefully, no, just occasionally crash, okay. Walk into a world of reliable bits of software. Here we go. So because I'm using Linux, the availability of this sort of software is a little bit more limited. GQX is nice enough. On Windows, you can get SDR Sharp and some other things, which are probably worth looking at, but I don't know much about. So here it's scanning 434 megahertz. I've actually hooked it up to my Blade RF, so it won't pick up very much of actual radio, but I do have this small handheld ham radio, and if I transmit briefly on this, you can see some spikes where my radio's transmitting. If we zoom in a bit and set it to the same frequency and tell it I would like to decode narrow FM, which is what my radio transmits, testing, 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 then I'm not sure, could you hear that over the speakers? No. I'll turn the gain up. Testing, testing. Maybe. In any event, you can certainly see that it's picked up some audio from my voice there when I spoke. So this is kind of a nice common way of doing software-defined radios. You can just hook up your receiver, you can scan across huge swaths of bandwidth and see anything that's going out over the air. If I plug in an actual antenna, we can probably start seeing a whole bunch of junk which is just floating around. I know that there's the ham radio people doing their exams upstairs, so if we got the timing just right, we could probably listen to them chatting. There's the UKHAS net nodes in the lobby, and all the normal rubbish that otherwise occupies the band. So let's see, cranking up a bit. There's not very much going on here. Let's try 869 500. Nope. So here we go. This is a UKHAS net packet, and this is someone on a similar frequency spamming quite regularly something else. Oh, and that was another UKHAS net packet perhaps. So if we zoom in a bit on this part of the spectrum, at the top we have the kind of, I should have explained this at the start I guess, the frequency running across. So you can see how much signal is received at every different frequency across, in this case, a couple of megahertz of bandwidth. So this is a lot like the balloon transmissions. It's swapping between two frequencies very quickly to send us some information. We can't usefully listen to it on audio just because it's not that sort of signal, but we can try anyway. And you can kind of briefly hear these pulses of data as it transmits something. Where else? If we look at Wi-Fi sorts of frequencies, Not at the moment, apparently. Typically, you'd spot some Wi-Fi activity going on. Okay. So this is kind of well and good if all you want to do is receive something, and for a lot of people using software-defined radios, this is enough. You can use this to listen to your hub and send the audio it receives into DLF or Digi to demodulate. Usually it's more interesting to I think it's more interesting to kind of do something yourself with that. So if I hook this back up to the Blade RF, and plug it in. I'll stop this. So, GNU Radio allows you to very easily interface with these things. We'll just say we have a source, and we'll tell it to use the SBY as our source, and we can tell it, I want you to sample at 2.5 million samples a second and tune to 434 megahertz. E is just shorthand for like times 10 to the power 6, which is million. We can choose some gains. I'll just turn all the gains down because it's connected directly. Hit OK. And now when I run this, real data will stream out of this blue port here into whatever I plug it into. So immediately we can just plug it into a frequency thing, the sort of thing we were looking at before. And set it to the same setting. Okay, and now we can see what the SBY is receiving. And again, if I were to transmit, you'd probably, there we go, you can see the same spikes from my handheld. So that's nice. But we can also now grab a sync, which is something that's going to transmit. And we can tell it to use the Blade RF. And again, we can set some sample rate. Here I'll just go for 1 million samples a second. Set it to the same frequency. We can mostly leave these off. Oops. Let me set this one up a bit. Okay, and now we need to generate something to send into it. So to start with, we could just do a sine wave. Here's some sine wave. Will allow us to set the frequency again, so we can see what happens when we change it. So we drag a little slider on. We'll change it between 0 and 10 kilohertz, say. We should do. And then we can just connect these together. And here we go. So that's kind of noisy. If I increase the frequency here, you can see this spike along the bottom, which represents the kind of incoming signal through more noise than is strictly reasonable. I'll try. Only on its received for transmits going directly. The Blade RF is hooked up to the SBY through an attenuator. Okay, and then just wait a second for it to sort itself out. There we go. So okay, it was a bit noisy, which means we probably want a bit more transmit power coming out of the Blade RF. Set this to like -4. And try again. Still not great. Never mind, I'll go with this. 6, 10 maybe.
Yeah, I always find those have to be turned up quite a bit before you get anything out of it.
Yeah, oh, that's much better. Okay, so here we go. Here's the signal that we saw. It's just a sine wave, so it just appears as a single kind of peak in this frequency. So we can see all the frequencies it's receiving down here. If I drag this from 0 up to 10 kilohertz, very little happens. Oh, joy. Well, let's try increasing it to something a bit more substantial, like 1 megahertz. Solid as rock. Well, good. Here's one I made earlier. Where is the one I made earlier?
It was working just earlier when you tried it and it had more noise. It was working correctly.
Yeah, I know. Yes, it is. Oh, that is mysterious. Let's try changing the amplitude. So here we can multiply this signal that we're generating by some constant. And we'll choose what the constant is again, calling it amplitude. And we'll add another slider. And this one can go from 0 to 1.
Adam, should under signal source frequency 0, should that be frequency equals 3?
This one? This is because it pre-computes. So frequency is set to 0. Yeah, it's kind of a bit confusing. It would be nice if it showed the variable, but it doesn't. But let's see what happens if we... Okay, so it's just sat there constantly.
Unplugging and plugging back in the...
Yeah, that is not a terrible idea.
Speed driver.
How do I transmit one? Just to... Yeah, fine. We'll unplug them and plug them back in. Hey, that's better. So now if we increase the amplitude... No, oh, it's still horribly broken. Maybe we'll just swap to using real antennas. So strictly, you have to be a little bit careful with what you transmit with SDRs, especially when you have transmit capability, because they will not stop you transmitting in frequencies you're not licensed to transmit on. In this case, we're operating in an ISM frequency where we are allowed to transmit, and these only put out 10 milliwatts, so we're not doing anything naughty. In more serious cases, you might want to start thinking about using an amateur radio license, or not using antennas at all, and then it doesn't matter so much. Sorry. Okay, let's try that. Well, that is still very disappointing.
Frequency mode.
Let's try this one. That's quite interesting. So in this case, we're now outputting what we receive to the speaker instead of just the screen. And I guess that means if we... Testing. Great, so this is just using the S-by now. And just like in GQRX, we're tuned to some channel and outputting whatever comes out of this, in this case a narrow band receive block, into an audio sync. So it's fairly straightforward. And yeah, if we key up here, then you can kind of hear whatever I'm saying and you can see it on the spectrum at the same time. So at one point I had a really good flowchart which loads an audio file and then transmits it out the blade RF and receives it into the other one, but I guess that is not going to work so well. Okay, there's one other fun thing to try then. So because you can transmit pretty much anything you want on these radios at any given frequency. That's weird. I guess I see what the problem was. Well, that'll do it. Fun failure mode of GNU Radio is that if it can't find a sync, for instance, your blade RF has become disconnected, then it will just load up a dummy sync instead. And I suspect if we scroll up, here we go, failed to open blade RF device, filling up one missing channel with null sync. So it was actually just writing all our signals into null, which was unhelpful. But never mind. If we load up GQRX again, let's see. Bam. So what we're doing here, let's zoom out of it, that's with grace, is transmitting on a bunch of frequencies at once. And if you transmit on the right frequencies over time, you can get this kind of amusing effect where you paint the spectrum. So it's in many ways quite straightforward. At any moment in time, you want to transmit one line of this image, and you break that line into pixels, and each pixel is one frequency. So all you need to do is see which pixels are on for each line, and then generate a signal at that frequency, and you add them all together, and you transmit that. And then when it receives, it shows you what frequencies were present. So whenever you are putting a frequency in, you get it out on this. And yeah, ta-da. So this does actually mean the blade RF is working again. So if we turn that off, we can probably go back to the much less exciting demo where we just... Christ. Well, I guess now the S-Play is not working. Fantastic. I'm not going to say this isn't uncommon. Some of your time will be spent recompiling GNU Radio when it just doesn't work, or you need to change versions, or like your version of libhackrf is different from the version of GNU Radio you're running. Here we go. This is a bit more promising. So, okay, right. So we have an amplitude control, which is just going into this mixer, this multiplier, sorry. And if we increase that, we can change the amplitude of the signal. And we have a frequency control, and as we shift that, you can see the frequency goes along. Now, there's a very confusing effect going on here where the frequency is clearly existing at many, many different locations. This is because we're transmitting at far too high power into an antenna that's right next to us, and it's distorting massively. So previously with the attenuator, you probably wouldn't have seen this effect. If you look carefully, you can even see little spikes going the other way as I change the frequency. So... No, this is the main carrier. Okay. And then if I shift up even just a little bit, there goes the main carrier, and here comes one just like it in a whole little parade.
Is that aliasing or harmonics, or just some antenna tuning thing I don't know about?
So it will be, the transmitted signal is too strong, and on the receiver it's kind of distorting the incoming sine wave, which makes it look a bit more like a square wave. And the square wave has many harmonics of the same frequency, so that's what we're seeing here. The reason you see smaller ones going the other way is because it kind of keeps going into negative frequency, and those ones look like they're going the other way as we increase one frequency. So, I mean, that was most of what I wanted to show off. The GNU Radio is... I definitely had a really fun audio one, but apparently not anymore, so here we are. I probably just named it something stupid. But... I guess not. Oh, there we go. I don't know what the timing schedule is like, but no one's coming to kick me off, so if anyone wants to chat or talk about this or have a play, then feel free. Otherwise, I might set up this audio transmit receive thing, and then you can kind of transmit WAV files and pick them up on the handheld radio, which is quite amusing too. But otherwise, I guess that is everything I came to say, so thank you for listening.
Daniel, I think this is it. Are we going down the pub? Do you know which pub we're going to?
The cheap one, right?
We'll go to the
Marlborough Arms, which is literally just up the road. So.
Okay.
I'm
Well,
sure we'll end up going
I'll go and pass the word
Frequency.
round. Marlborough Arms. Okay. Right, well, this is the end of the sort of formal UKHAS session. I'm sure people will be hanging around and chatting. So, thanks all for coming. Cheers.